Hi everyone, and welcome to our module on neural networks. Neural networks in data science are modeled on how our brains work. As you can see here, our neurons in our brain consist of nodes that aggregate information that come to them from dendrites, these little thread-like architectures here, and then pass the aggregated information on through an axon, a brain stem, to, in fact, as we can see on the right side here, other neurons through connecting with dendrites, and those connections happen through synapses. In data science, neural networks look very similar. Our neurons in data science get information from dendrites and then pass this information on after aggregating it through axons that connect to other dendrites that then again are connected to other nodes with aggregators that pass information once it is aggregated and processed on to other dendrites that are connected to other neurons. Now, it's important to understand that some of these connections between axons and dendrites contain higher weights than others because some connections just make more sense than others do. Let's take this example on the right side here, where we see sunglasses, eyeball, and eyeglasses. And we're seeing that some of these connections make more sense than others. For example, eye and ball makes eyeball, but eye and sun, eye-sun does not make sense. However, the connection between sun and sunglasses makes sense, which is why it is shown here as a thicker line than the connection between eye and sunglasses, because there really is not much of a connection. This is why it is shown as a thinner line. So the connection between eye and eyeball carries more weight because it makes more sense than the connection between eye and sunglasses, which carries less weight, shown here as a thinner line, because it really does not make any sense. Now let's see how these concepts translate into neural networks in data science. A neural network typically consists of an input layer and an output layer. The input layer models the feature space of our data set, that is, all the X attributes or the input attributes in our data set. And the output layer is the class membership or the Y attribute in our data set. In the middle, we have a set of neurons in 1, 2, or more hidden layers that are connected with the outputs of the previous layer. And these connections carry weights, just as we saw with eye, sun, and eyeball. In between, we have bias nodes that allow us to tune the functionality of each of these hidden layers. And the goal of our neural network is to minimize the error in class assignation at the output layer through continuous reevaluation and optimization of the weights and the biases. This is also called an optimization of the loss function. Now let's zoom in on our neural network. As we're seeing here, a neuron is a computational building block for the brain in which dendrites funnel information into a nucleus. The information is processed and sent on through an axon into other dendrites to other neurons. We have the same model in our artificial neuron here, in which we get output from an axon, just like this here, through a synapse that is modeled by a weight that then connects through a dendrite to our neuron, our cell body, which we see here, together with input from other axons as well through dendrites. In our cell body, we perform a summary function of all the inputs and then an activation function that processes the aggregated information and then sends it through our output axon into the next layer. This is what we're seeing here. So imagine this cell body being one of these circles right here. So we're getting our X's here in our input layer. We're seeing here in our output layer our final neuron and our Y, our class membership. And we have our weights here and our biases, which are shown at the bottom. Now each layer, as we see here, aggregates the information from the previous layer and then applies a function to it, and the form of this already gives you an idea what kind of function we're looking at. Then we have another weight here, and in our output layer, finally all the information, all the output is aggregated and processed one more time. And as we calibrate our neural network to minimize that loss function that I spoke of earlier, we use two processes. One of them is called feed forward, and the other one is called backpropagation. Let's look at that next. Here is what goes on inside of a neuron. Typically, at the beginning, all weights are initialized with random values because we're optimizing them later anyway. Then we feed the input tuples into the network one by one, and we aggregate all these inputs, which means we compute the net input as a linear combination of all the inputs. And then we compute the output value for this one neuron using an activation function. This is the feed forward part here. This is the activation function. And then we can also compute, of course, the error. And as we have computed the error, we are going to update the weights and the biases. Now, computing our initial Y is called feed forward. Evaluating our error and adjusting our weights and biases, that is what is called backpropagation. And our goal, again, is to obtain a set of weights that helps us optimize the correct classification for the greatest number of tuples in our training data set. And now, let's get up close and personal with the neural network and look at an example. Let's start with our feed-forward process. This is our data set. Our data set has two input attributes, x1 and x2, 4 tuples, and one output class that is either 1 or 0. And we will specifically look at our fourth tuple here, with x1 being 1, x2 being 1, and our y being 0. We've architected a hidden layer consisting of 3 neurons, and we see that each one of our input attributes connects to each of the neurons, and each of the neurons sends its output to the output layer and eventually is supposed to resolve in 0, which we know is our output. We start by applying random weights, since this is our first forward propagation. We're seeing here 0.8, 0.4, 0.3 as initial weights for x1, and we're seeing 0.2, 0.9, and 0.5 as initial weights for our x2. We're seeing here as well 0.3, 0.5, and 0.9 as the random weights for the connections between our hidden and our output layer. So now let's do the math. For our first neuron here, we are multiplying 1 times 0.8 and 1 times 0.2, which gives us in sum 0.8 plus 0.2, that is 1. We do the same process with multiplying 1 times 0.4 and 1 times 0.9 for our second neuron. 0.4 plus 0.9 is 1.3. And we multiply 1 times 0.3 and 1 times 0.5 for our third neuron. 0.3 plus 0.5 makes 0.8. This is our first summary aggregation. Now we need to apply our activation function. We apply our activation function to the sum that we have just calculated here, And we have the option of choosing one of several of these activation functions. In our example here, we're going to use a basic sigmoid function, which we are already familiar with from our logistic regression. So if we apply the sigmoid function to our 1.0 that we've calculated for the first neuron, we receive an output of 0.73. If we apply the sigmoid function to our 1.3, which we have calculated for our second neuron, we receive 0.78 or 0.79. If we apply the sigmoid function to our third neuron, for which we have summarized 0.8, we receive about 0.69. So now we are going to calculate the input for our output layer here. This is the 1.235 that we see right here. It is the output of our aggregation or of our summary function for our output layer. And now, just as we have done with our hidden layers, we apply the sigmoid function. We can use the sigmoid function calculator if you want. Here is the link to calculate the output from our activation function for our output layer, which is the sigmoid function applied to 1.235, and the output is 0.77. Now we know that our target is 0. Our calculation gives us 0.77. This means that we have room for improvement. We need to change our weights here in order to get our calculation closer to 0. This is where backpropagation kicks in. We start our backpropagation by calculating the output margin of our error. Now we know our target is 0. Our calculated result is 0.77. So our output margin of error is minus 0.77. Our next step will be to take the derivative of the activation function, which is our sigmoid function, and then apply it to that output sum. So our delta of the output sum is our derivative of the sigmoid function for our sum multiplied by the output sum for the margin of error. This means we apply our derivative of the sigmoid function to 1.235, because that was our output of the summary function, and multiply it by minus 0.77. This means the delta of our output sum is minus 0.134 and so on. Now we can adjust our weights. We know that the hidden result here of our first node is 0.73. The hidden result of node 2 is 0.79, and the hidden result of our third node is 0.69, thereabouts. So with this information, we can calculate the amount by which we need to adjust our weights. To calculate our delta for each of these weights, we divide the delta of the output sum by the results of the hidden layers. So in other words, we take our minus 0.1344 and we divide it by 0.73, by 0.79, and by 0.69, which means that our old weight, number 7, of 0.3 is adjusted by 0.1838. So our new weight 7 becomes 0.1162. Our old weight 8 of 0.5 is adjusted by minus 0.1710, so that our new weight 8 becomes 0.329, and our old weight 9 is adjusted from 0.9 by minus 0.192 to our new weight 9 of 0.708. Now we can enter our new weights right here. But we're not done with our backpropagation just yet, because we still have to adjust the weights between our input layer and our hidden layer, which means we have to recalculate the sum here and then also the output of our sigmoid function. To do this, we will follow pretty much the same procedure as we did before by applying the derivative of the sigmoid function, this time to the hidden sum. Previously, we did that to the 1.235. So we're going to divide the delta of the output sum, which we already know and have calculated as minus 0.1344, by the product of the hidden to outer weights here, and multiply that by the derivative of the sigmoid function for our hidden sums 1, 1.3, and 1.8. So this gives us here, if we calculate that out, minus 0.448, minus 0.2688, and minus 0.1493 times, and then the derivative of the sigmoid function for our first hidden sum is 0.1966. For our second sum is 0.1683, and for our third sum here is 0.2139. So now if we multiply that out, the delta for our hidden sums is minus 0.088, minus 0.0452, and minus 0.0319. So now that we have the delta, that is the amount by which our input weights have to change, we have to set them in relationship with our input attributes here. Luckily, those are 1 and 1. So if we divide the delta for our weights by the values of our input attributes, really nothing changes much. So that our old weight 1 of 0.8 is adjusted by minus 0.088, and our new weight 1 becomes 0.712. Our old weight 2 of 0.4 is adjusted by minus 0.0452 and becomes 0.3548. Our old weight 3 of 0.3 is adjusted by minus 0.0319, so that our new weight 3 becomes 0.2681, and so on and so on. We do this for the next nodes as well. And with these new weights, we can launch another feed-forward cycle and use our new weights in order to calculate again our hidden sums, apply our sigmoid function, and then arrive at a new output value. Now again, our target is 0. Our calculated value with our new values here is 0.69. So we should probably optimize again and follow our backpropagation procedure again. This is how we start optimizing our neural network, how we start optimizing the weights in our neural network, and how we start minimizing the loss function, that is the error that we see between our output that we have calculated in our neural network and the actual target value that we know. So what are our takeaways here? We have seen that through backpropagation, we can iteratively adjust the weights that sit in between our layers so that we can optimize our output, our loss function, as we said before. But we also understand that that can take a long training time because we have so many iterations that we need to perform in order to arrive at our optimal number. So how can we cut down on the potentially long training time, especially if we have a large number of input attributes in our input layer? Well, we could either decide that we limit the number of iterations in our neural network, or we could adjust the ways in which we optimize our weights. And this is where gradient descent comes in, and the whole idea of optimizing our what is called the learning rate of our neural network. This is what we will talk about a little bit later, because first we want to also understand what we can do in order to optimize the functionality of our neural network by looking at the different kinds of activation functions that we have available. Here we see the three most popular activation functions. The sigmoid function we've already looked at. It is one of the most popular functions here. We're seeing that the gradients disappear here, but we also see that it starts at 0. It is not 0-centered, so the outputs are between 0 and 1. That can pose a problem. Here we're seeing the derivative of the function that we applied during our backpropagation. Now, an alternative to that is the tan activation function. We're seeing here is 0. Here's the 0 line. So our tan activation function is actually 0-centered, and it has vanishing gradients, but it is larger, and its output typically lies between -1 and +1. Another very popular function is the ReLU activation function, which typically gives us a binary output, because every input that is less than 0 results in 0, less than or equal to 0, and then every input that is greater than 0 results in the input itself. So the derivative of the ReLU activation function is this one. It is either 0 or 1. Now, there are attempts to fix this whole problem with any input being less than 0 resulting in 0. These efforts are typically called the leaky ReLU or the randomized ReLU function, that apply a small coefficient to this leg of the function, typically 0.01 in the leaky ReLU function. Everything else is called randomized or anything other than leaky ReLU, in order to really not turn any value that is less than 0 into 0. The reason the sigmoid function is so popular is that because we're seeing its result between 0 and 1, we're of course looking at probabilities here. This becomes very useful for our output layer, in which we calculate the probability of class membership. This is why in an output layer, typically we have a sigmoid flavored function available to us. This is very often also called our softmax function, which is a more generalized logistic activation function used for multi-class classification. But what's hiding behind the softmax function is really a type of sigmoid activation function. And of course, we also have to talk about the loss function. Remember, the loss function is our error correction. That is the difference between the calculated output that we see at the end of a feed-forward process and what we call the ground truth, which is the truth that we know. For example, in our first neural network output, it was 0.77 versus 0. So for regression, of course, our loss function is the mean squared error. We've worked with that before. And for our classification, this is called the cross entropy loss. We've seen that before as well. All of this brings us back to our backpropagation, in which we compute the error in our forward pass, apply our loss function to determine what we are using as the basis to compute the gradients in our backward pass. And then we subtract the fraction of our weight's gradients from the weight itself, which we have done. And that's what we call the learning rate. Now, that learning rate is what can make or break a neural network. How to optimize the learning rate is what we will learn now as we talk about gradient descent.